Yes, sir. Good afternoon. Welcome to MPLS. We're going to get started now. Please have a seat. I apologize in advance. I'm feeling very cranky. I don't mean to take it out on you. Next slide, please. This is our note well. Please be professional. By now, I assume you've already read this. Here's all of our administrative stuff. This is our agenda for today. Anyone have any comments on the agenda? Okay. We have no new errata. We did have one incoming liaison statement. This is work on MPLS TP. And Adrian is flinching, understandably. We did not reply to this. Document status. We have 2 new RFCs. Yay! Forward progress. We have filled up the RFC editor queue quite successfully. They are now the bottleneck, not us. So. And we've got 2 more on the way. Framework draft, that's actually at 12 now. And first nibble draft. Those will be coming out soon. No new docs right now. We have several updated docs. The MPLS M&A header, that is the ISD header draft. Our second working group last call failed. I have not heard a whole lot of responses from the authors about this draft, and this is deeply concerning. There are some strong opinions that have been expressed, and you have not responded. We would very much like for you to do something. And I will point out that this is now a working group document. If you choose not to act, the working group chairs can and will replace you as authors. Please do something. Okay. And we've had a couple of things expire. We have a handful of new documents coming in. And lots of alive individual documents. In particular, we should talk about IOAM decks. We had just completed 2 adoption polls. Both of those adoption polls passed. One for doing things with ISD, one for doing things with PSD. Both of these are for the same topic. Therefore, the working group chairs have asked the authors of both of these groups to collaborate. Let's please combine into one draft. We have not heard a response from you yet. We would appreciate it if you guys would.
I'm Greg Mirsky-Erickson on behalf of authors of one of the drafts. I already reached out to Rakesh and we will work on it. And thank you for your decision.
Not our decision, it's a working group's decision. So thank you very much. We look forward to some output soon. Draftly MPLS M&A entropy that did not pass adoption, and therefore this is going away. That's all on document status. Let's jump now to our agenda. First speaker is Fabian.
Can I take that mic, or is it fixed?
Should be able to take that.
Okay, yeah. So can you hear me? Does it work? Yes.
Okay, so my name is Fabian Ihle. I'm a PhD student from the University of Tübingen in Germany. And my first talk is about our latest, or our new internet draft called Stateless M&A-based Egress Protection, short SMAP. Some introduction before that, some background knowledge. We have the MPLS egress protection already, like the framework defined in RFC 8679. And there we establish bypass tunnels for egress routers on an egress failure, like mostly on an egress node failure. Now, that bypass tunnel relies on a point of local repair, which is mostly, or normally the penultimate node. And that node has to do failure detection and a local repair mechanism, like it has to do some rerouting of traffic. In that PLR, we have to maintain a mapping of, let's say, transport tunnels to that bypass tunnels. And those have to be signaled between the egress node, the protector node, the ingress node, and the PLR. So here you see an example. We have an example topology here with 3 labels or 3 segments. And now if the egress node C fails, we have a bypass tunnel, which is here in that forwarding table. That basically says if there's an incoming, let's say, label C, do a bypass tunnel using the label C prime and C prime prime. So in this case, it's a segment routing bypass tunnel. Also, this is basically a simplified example. And now that's where the stateless M&A-based egress protection idea comes in. Our idea is to fully eliminate the need for state in the PLR, because we can move that information we have to have in the network there into an M&A network action, and that's the idea behind that. Then we can eliminate the state from the network and just have that state on the ingress node. But as we have signaling with the MPLS egress protection framework anyway, we can just use that information we have at the ingress node. And therefore, we do not need that mapping table, and we also do not have to involve the PLR into signaling in any way. Now, basic idea is the PLR detects a failure and uses the bypass MPLS labels, we call them BML for now, from the network action to reroute the traffic on an egress failure. That's our proposed network action encoding. We need 20 bits of MPLS label, so 20 bits of ancillary data. We decided for instack in this case. 20 bits MPLS label means we have to use a format C LSE that does not fit into a format B LSE. So fortunately, format C LSE has 20 bits, so we can just fit in 16 bits here and the remaining 4 bits here, and we have our encoded bypass labels. Optionally, we can also encode segment routing bypass tunnels in the network action. There we have format D LSEs, which we can just append to the format C LSEs. We waste a few bits around here, as we have a lot more data bits available in the format D LSE. So for now, we say that you have to set the most significant bits, the 2 most significant bits of the first data field to 0 and the second data field as well. And then we can have that 20 bits bypass label in a format D LSE. So how does the network action actually work? First of all, the ingress router has the knowledge about bypass tunnels, like it's signaled prior to that, just as done in the MPLS egress protection framework. And now the ingress router has to place an instack network action with the select scope for the penultimate node, so for the point of local repair. And that ensures that only the penultimate node will actually execute this network action. Note that we still require signaling between the egress protector and ingress node, just as we do with the MPLS protection framework, but we do not require signaling to the PLR anymore. Now, if the PLR detects a failure, like an egress node failure, the process is as follows. Like, we have to extract the BML from the AD of the network action. Then we pop the incoming MPLS label, but that depends on the setting. We push the BML onto the stack. Like, basically, we swap the incoming labels with the BMLs. We also pop these network action because it's a select scope network action, and the forwarding label on top of that is popped. And then we forward according to the top of stack label. So according to the bypass label. Okay, here you have a short example. It's the same topology you've seen on the first slide. So here on the, left side, that's the pushed MPLS stack by the ingress router. We have, let's say in this example, 3 labels, A, B, C. Each label represents 1 segment and is popped by each node. And we have the select scope SMAP network action at the bottom. In this case, at the bottom of stack, but it's in scope for the penultimate node. So now the packet that arrives at the PLR has only the label C on top in this example. And it detects that the egress node C has failed, therefore performs the SMAP network action as indicated in the MPLS stack, and moves the bypass labels C prime, C prime prime on top, and then we can reroute based on that label to an alternative protector egress node. Okay, just for completeness, security and IANA considerations, we use the mechanisms described in the M&A header encoding draft and from the MPLS egress protection framework. So those also apply to this document. And for IANA, this draft requests the allocation of a new network action opcode for the stateless M&A-based egress protection network action. So there's plenty of time. Next steps would be questions, comments, discussion about it. Is that a relevant use case? I'd like to hear opinions. Thanks.
Greg Mirsky, Ericsson. Thank you for presenting it. It's very interesting. I wonder if you thought about generalizing this approach for local protection in general, not just in egress protection.
Yes, I did actually, but for like transit nodes, we already have plenty of mechanisms like fast reroute we can just use. But the special case with the egress protection is that we do not have a next hop we could use for that. So
because it seems like this might be really applicable for SRMPLS, where you can do this local protection and do the programming, because then it's kind of logical for the paradigm of programming from ingress, so that you present everything, all alternatives in your label stack, because it seems that it might be working, maybe needs a little bit tweaking,
yeah,
but it's interesting idea.
I guess the only change you would have to do is the name, of course, because it's stateless egress protection. And then you need some more signaling for transit nodes. Maybe, I don't know, maybe that's already signaled.
Yeah, but again, generalizing might be interesting, you know, if you can really apply the same mechanism to more cases.
Yeah.
Makes it things simpler. Thank you.
Thank you.
Sasha?
First of all, I have a question. Maybe I have missed something, but your encoding only mentions the label that should be used to send traffic to the next hop towards the protector. But this is not enough, generally speaking. You also would like to know how do you I think that you need to specify the interface of the interface towards the next hop of this processor, or the next hop itself, whatever. Otherwise, it is not. If, for instance, your PLR has multiple interfaces in addition to the interface towards the failed egress node, primary egress node, how would you know? How would it understand towards which node it should send something? And the second point that I think that basically this should work just fine with segment routing, because effectively what the protector should do, it should send the packet with the node SID of the protector towards the appropriate next hop, and this it would reach the using the SID label that represents the SID of the protector node at this next hop, and that would be just fine. So I think that my guess, not that I have thought about it more deeply, it looks like this should be very nicely tuned to merge with this with segment routing. And in any case, well, Spring work group had already had this session here, but I suggest that you, I think that presenting this proposal to Spring makes plenty of sense to me.
Yeah, that could be also interesting to them. Yeah, right. Thanks.
Hello. So I have two points. First of all, I wanted to pick up on Greg's point about generalizing this. The problem with generalizing this is that you would need this repair strategy encoded in the packet for every hop along the way, and that just simply does not scale in terms of stack size, because any of the nodes could fail. So I think you are right to rely on traditional methods for fast reroute on the path up to the special case of the edge node. But I would put it to you, there's an alternative strategy you could apply, which is that instead of encoding the labels rather strangely in this header, what you could do is have a different action at the penultimate node, which is basically pop n. So if you manage to succeed in delivering it, then you pop n of the following labels, because you're not going to need them. But if you need the alternative routing, you pop the action label only, and that gives you a set of labels that would steer you round to your alternative exit. And that is far more sort of MPLS friendly around the PLR that's having to do this. It's much more within scope of MPLS. It's not having to go and rebuild a whole bunch of labels into a different format. I can write this up for you if you like.
Thank you.
Jidong from Huawei. The first question is about the encoding. If this opcode is the only one in the ISD, does it mean that format B will be wasted?
Yes, actually, yes. That's also what you see in the example here. In this example, I set a wildcard for the format B opcode. We have to have it in the NAS because that's mandatory in the encoding draft. But you can, of course, use it with the opcode 1 for flag-based actions, for example, like having another no further fast reroute bit set or something like that. But if you're not doing this, for now, it's wasted. That's true.
Yeah, okay. The second one is about the scope, how you control this. The PLR will pass this opcode not by other nodes. Is that you need to specify the position of this MNA substack in the packet label stack?
Yes. I mean,
if you have multiple PLRs on the path, does it mean you need to have multiple NAS substack in the packet?
Yes, but I guess those different PLRs will also have different bypass tunnels then, so you need different NAS anyway.
Okay, but that means you will have some more waste of this label stack entries, right?
Yeah, I mean, it's a trade-off between having kind of bloated packet headers and having no state in the network. That's a trade-off, yes.
Like you have multiple, this M&A label carried. This is something. Yeah, I know. Just want to understand how it works. Okay, thank you.
Yeah. So, queue is empty, I guess. Okay, then thanks for the feedback. I'd be happy if there's some engagement, discussion on the mailing list about that. Maybe also just summarizing for today. Thanks. Okay, then I'm just on time for the next talk. The next talk is an implementation update on our P4 implementation of the M&A framework. This time it's only about using instack data. I already presented a more general version in the last interim meeting, but since then a lot has changed. So first of all, some motivation why we are doing this. So motivation is still the same. If M&A wants to be successful, it must be efficiently implementable in hardware. And it's a pretty similar use case than IPv6 extension headers. And there's a lot of evidence that in some cases, those extension headers are not supported very well on hardware, like they do not scale very well. So we as researchers, we use the Intel Tofino 2 as a reference architecture for hardware switching ASIC. That's a difference from the interim meeting. There we only had an Intel Tofino 1, and now we basically have a bit more resources and more line rate. So on the Tofino, we have limited resources and limited number of operations we can apply. So it's a lot of acrobatics with table structuring and stuff like that, but we can still operate at 400 gigabit per second per port. And we say that if we manage to implement the M&A framework on our P4 hardware, which is very constrained, you hardware engineers and vendor ASICs and all you people will have no problem implementing it as well. And also note, we are doing research. We do not build commercial M&A hardware, so just keep that in mind. So the next few minutes are about P4 M&A, and the implementation has basic MPLS functionality like popping, swapping of labels, forwarding accordingly. And also we process in-stack data, M&A network actions that are in scope at an LSR, meaning in the select scope NAS or the hop-by-hop scope NAS. So questions for the next slides are, how does the implementation work? I will keep that very briefly. And what are the actual capabilities of our implementation? So I have only one slide about the implementation, as I actually do not want to bore you with technical details. If you are interested in that, just ask me afterwards or read our preprint paper. So first of all, on the Tofino, we have to parse all relevant LSEs before we can process them. That's an important constraint. We cannot just hop between parsing and processing. It's maybe different in other hardware. So parsing is not that easy with the M&A framework, but for this talk, I'll just keep it to it works. After we parsed our network actions, they have to be executed, of course. And that's done by applying match action tables in the pipeline. So we have one match action table per LSE in a NAS. That means as we have up to 16 match action tables, 16 LSEs or 16 network actions in a single NAS, we need 16 of those match action tables. In each match action table, each LSE in the NAS is matched to that table according to its opcode and its network action length field. Actually, it's a bit more complicated. There are also more key fields we match on, but as I said, more details about that in the paper. Now, we have to implement 16 match action tables for a single NAS. And fortunately, we have exactly enough resources to fit 16 of those tables into one pipeline iteration. If there's a second NAS present, we have to resubmit the packet. And after resubmit, we can process the second NAS. That's also a difference to the MPLS or the M&A implementation from the interim meeting, because since then we did some tuning that we can do a resubmit. Back then we had to do a recirculation, and the recirculation costs us bandwidth, meaning we have to reduce our line rate or we get some additional latency depending on the resources we have available. So with using resubmits, we can process 2 fully sized NAS at line rate. And we verified this actually in 2 evaluations. First of all, a performance evaluation where we have like a dummy network action that verifies if the implementation works at line rate. And then we have another use case evaluation to show that it's actually capable of not just dummy actions, but of a use case or an individual draft described as use case in the working group. Okay, so first of all, for the performance evaluation, the goal is to verify if we can actually process 2 NAS in line speed. And for that purpose, we define the dummy network action, and the dummy network action just writes arbitrary values into the AD fields of format B, C, or D LSEs. So you see it here in the picture on the bottom, on the top right. Let's say dummy network action opcode X is sent into our implementation with an empty AD field. AD fields are filled, and then we can look at the packets and we see there actually happened something. And we can verify, depending on the data, or that there's even data present that the network actions were applied. So for experiment setup, we used our traffic generator P40G. It's also Tofino based. And there we send 100 gigabit per second of traffic to our implementation. P40G supports a maximum stack of 32 LSEs for now. Actually, it's 15 LSEs, but we extended it for this evaluation. And in the MPLS stack, we have 2 NAS present, one in select scope and one in hop by hop scope, each filled to the maximum number of network actions that the traffic generator supports. So that's what you see here on the right. We have 2 NAS, we have the format A for each NAS, and then we have format B and 13 format C network actions. That means in this evaluation, we have up to 14 network actions. Or not up to, we have exactly 14 network actions. For the result, I'll keep it simple. We measured the received traffic rate with P40G, so we had a kind of feedback loop from our P4 M&A implementation back to the traffic generator, and there we could verify that we actually achieve line rate and that we have no packet loss. So everything was processed in line rate. Further, we also verified the content of our ancillary data fields in the network action by looking at them in our Wireshark dissector. Like, we also built a Wireshark dissector for M&A traffic, and there we could actually see that the network or the ancillary data was inserted into the packets. As I said before, P4 M&A actually works on 400 gigabit per second and supports fully sized NAS, so actually 34 LSEs only for NAS, but our traffic generator does not yet. We actually got a new one last week, but I just didn't have time to set it up. But I'm pretty sure it will also work with 400 gigabit per second, because on the Tofino, it's like if you get your program to compile, it will run at line rate, except if you're doing recirculation, and we're doing not recirculation, so it will also work most likely. Okay, so next evaluation was an actual use case evaluation we did. There we implemented packet loss performance measurement with the alternate marking method. It's based on the draft you see here in the bottom left corner, the draft CX, MPLS M&A in-band performance measurement. Here you have the simple concept. I'll just describe it very briefly. Like, the concept is that you send alternating colored batches of packets through your network. And in this case, like in the draft, the color of a packet is contained in a network action. It's not specifically defined in a hop by hop scope network action, but in this case, it actually makes sense to do it like this. Then LSRs count the packets per flow per color, like they have in our case registers, and just count the packets, increment them. And if the color changes, those square you see on the slides are actually arrows. If the color changes, like from red to green, a message is sent to the control plane or the collector or some instance in the network with that packet counter value, the flow ID, and the timestamp. Now the control plane receives those messages from all routers in the network or along a path, and can correlate them using the flow ID and the timestamp in them, and can then simply calculate the packet loss based on those two values. So in this example here, we have, let's say, no packet loss on the incoming link, like on LSRA. Then the color changes from red to green. Therefore, the counter value is sent to the control plane. Then we have packet loss on the link between those two routers. And therefore, the value of the red counter, or the counter value of the red packets, is smaller at LSRB. And we can simply calculate that in the control plane. So concept is actually quite simple. Now for our testbed for the evaluation, we do not have like multiple Tofino switches for hardware evaluation available. So on our Tofino switch, each ingress port represents one LSR, like we just plugged in cables between ports and each port is a separate LSR. And to simulate the packet loss on each link, we configured those LSRs or ingress ports to have a packet loss drop probability with 10, 20, and 30%. Like first one has 10, the second has 20, and the third one has 30% probability to drop a packet. Again, we generated traffic at 100 gigabit per second with our traffic generator that contains the AMM packet loss measurement network action at the bottom of stack, this time using the hop-by-hop scope. That means each LSR will scan through the MPLS stack, see there's a hop-by-hop action, and execute it. That's what you see here on the bottom right corner. And also you see the SR MPLS stack, like with 3 forwarding labels, ABC, and they are popped by each LSR and then forwarded to the next port accordingly. So for evaluation, we measure the packet loss using the AMM network action in our control plane, and then compare it to the configured packet loss, like to those drop probabilities. And that's what you see here. Actually, only that red box is important. You can see we have a configured loss rate of 10, 20, and 30%, and the calculated loss rate with the AMM network action is basically equal to that. So it's rounded to 3 or 4 digits actually, but I guess it's pretty much equal, yes. So result from that evaluation is P4 M&A is not actually only able to handle network actions like dummy placeholder actions, but we are also capable of implementing our own custom network actions. So not just the M&A framework itself. Okay, then I also want to talk about a different topic, a result from the implementation, the RLD of P4 M&A. So in the header encoding draft, a NAS has a maximum size of 17 LSEs, like 1 format A, 1 format B, and up to 15 format C or Ds. At an LSR, there are at least 2 NAS in scope. A select scope NAS that's located directly below the top of stack forwarding label, and a hop-by-hop scope NAS that's somewhere deeper in the stack, but within the readable label depth. That means in hardware, if we want to support that, we have to allocate 34 LSEs only for network actions or for NAS. Our implementation has a readable label depth of 51 LSEs, and that's a value that results from the available resources we have on the Tofino. And the difficulty in P4 is that the parser must parse all the LSEs until the hop-by-hop scope NAS is found. So as you can see here in that picture, the hop-by-hop NAS is somewhere deeper in the stack. There's some parsed but unprocessed MPLS labels in between. That's the part that encodes, for example, segments for other LSRs or select scope NAS for other LSRs. They are not relevant for our current node, but we have to parse them to get to the hop-by-hop scope network action. So now with 34 LSEs required by the M&A encoding and the RLD of 51 LSEs, that means we have 17 LSEs remaining to encode LSEs for other stuff. Of those 17 LSEs, we need 1 top of stack forwarding label, and that means that this part in between can only be 16 LSEs large. And as I said, even if they're not relevant for our current node, we still have to parse them, and we have to allocate resources in our hardware for them. Okay, so in the P4 program, and I guess that also applies to different or to other hardware vendors, we have arrays that are allocated for each LSE encoding type. So it's not just one big stack or one big array of LSEs, of 51 LSEs, but it's rather a stack of differently encoded LSEs in different arrays. And as it's usual with arrays in any other program language, the size of an array must be known and fixed prior to the runtime. So we cannot dynamically change the allocated size of an array for an encoding type. So the observation, if you look at this stack, is that it's pretty obvious that 16 LSEs that encode all the segment routing labels or forwarding labels for other nodes and select scope NAS or anything else for other nodes, that 16 LSEs is not very much, given even a single maximum sized LSE has 17 LSEs. NAS has 17 LSEs. So question that arises here is, do network actions really require 17 LSEs at a maximum in a NAS? And actually, most of the currently considered use cases do not, or even a combination of those does not. Like, of course, there are some examples like SFC with a lot of metadata where you require actually that number of LSEs, but the most use cases don't. So question is, can we somehow reduce the maximum supported size of a NAS? If we do that, we have more space available in the hardware for that in-between stack, and we can like allocate more resources dedicated to that. And there we have two possibilities. First of all, we can reduce the supported maximum size of a NAS in the encoding, but I'd not do that. I really like the encoding. We've seen that it works, and there may be some use cases even now or in the future that require that number of LSEs in a NAS. So the alternative to that is to signal the supported maximum size of a NAS along with the RLD. And that's our proposal, because the M&A encoding draft right now says the node responsible for selecting a path through the MPLS network needs to know and consider the M&A capabilities and the RLD of the transit nodes. So RLD, of course, we know why we need that and that we need that, but what exactly are the M&A capabilities? And right now in the draft, it's not really defined. So I guess it's also something like supported network actions per node or something like that. But our proposal now is to also include the supported sizes of the NAS into the signaling. Like if we look at this example here, on the left, we have the stack for our implementation with maximum sized NAS, where we only have 16 LSEs in the middle. But if we say our implementation only does, let's say, no further fast reroute, so we only need 3 LSEs or even less, 2, I guess. So we do not need to allocate that many resources for the NAS. Then we can just say our select NAS has a maximum size of 8 LSEs in hardware, and the hop-by-hop NAS, for example, 10, because we want to do anything fancy else there. And then we have 32 LSEs that we can use for that in-between part. And that then allows like less powerful hardware, like legacy hardware in a brownfield deployment, to not have, or that hardware is then not required to allocate 34 LSEs for NAS, but can use smaller NAS. And it's signaled to the ingress LSR or LER, so the capabilities are known then. Okay, that brings me to my conclusion. So to sum it up, we successfully implemented the M&A framework using in-stack data this time in P4 with line rate of 400 gigabit per second. Our implementation has a RLD of 51 LSEs that can contain up to 32 network actions. In the implementation, we implemented and evaluated dummy actions to verify if those actions are actually applied in line rate. And we evaluated an actual use case like packet loss measurement using the alternate marking method. We then proposed to include the maximum supported size of NAS into signaling, because that's a result from our implementation we observed. And this then allows LSRs like transit nodes to support smaller NAS, and that facilitates the integration of less powerful hardware in, for example, a brownfield deployment. Future work will include the evaluation of a PSD implementation. We already have one, but we have yet to optimize it and evaluate it. And we also want to implement more network actions, for example, the IOAM tracing option, the DEX option, maybe the SMAP network action if there's enough interest. There are many use cases we can do. So if you want to collaborate on that, or if you want to see your network action, if you want to see it implemented in our implementation, just contact me, reach out to me. I'm happy about that. You can find the source code of our implementation open source on GitHub behind that link here. And more details are available in the preprint of the paper behind that link or behind that QR code. So yes, that's it. Any questions? And thanks for your time.
Hi, this is Jagan from Cisco. I have a question for you. Like this implementation, I guess it's based on the M&A header version 8, right?
Yes, exactly.
Okay, so you also implemented with the 5 and 5, right? Already, right? So like, is there any difference in the performance or anything you see between 5 and 8 because we changed some of the header fields?
I didn't completely understand the difference in
Performance or any issues or with respect to version 5 and 8?
Yeah, I know. In the intro meeting, we implemented version 5.
Correct.
And I actually do not have a picture of the old encoding in the presentation. I think the difference was that we can now have format D LSEs attached to format B LSEs. That wasn't possible before. Like we can have ancillary data for the initial opcode. And the number of AD LSEs is restricted to 8 per format C or B LSEs. That's the difference. We implemented it and it works. So the old version worked, the new version worked, but the benefit of the latest encoding draft is that we can actually carry ancillary data for format B LSE. And we were not able to do this before.
Okay, yeah, thank you.
Rakesh?
Rakesh Gandhi from Cisco Systems. If you go back to the one that says 51 LSCs somewhere, you highlighted an interesting problem there that you really need 51 LSC. You really need to look. Do you think that, so there's NAL is the network action length, and there is NASL, which is the length of the substack, which is 4-bit. That's where the 16 comes. Do you think it makes sense to change NASL to 3-bit to make it easier for parsing?
It will make it easier, of course, but it's a trade-off in having smaller NAS then.
So I think that's something we should discuss with the working group to see if that makes sense to change NASL from 16 to 8 and it's still acceptable, because you raise a good question that do we really need 16 of them? Because if you start to work on post stack, for example, and if you have really long stack, can we put some data into the post stack after the stack and alleviate some of these issues? But it's some discussion we should have.
Yes.
Thank you.
Thanks.
Kian? Kian, last call. Okay. Thank you for the folks. The queue is locked and we need to move on to the next topic. Please save your questions, and if we have time at the end, we could talk about it then. Next presentation is Rakesh.
Good afternoon, everyone. My name is Rakesh Gandhi from Cisco Systems. Presenting, it's a Spring Working Group document on performance measurement using STAMP for SR, and we'll present the SR MPLS data plane today. So I'm presenting on behalf of the co-authors. So agenda is we'll have a look at the requirements. Draft really defines measurement modes in SR and encapsulation for them. So we'll go over it. So as mentioned, the various measurement modes in SR, one-way, two-way, loopback, and loopback with timestamp. It's a network programming. That's where M&A comes in. And various encapsulation. So draft does talk about links and SRMPLS, SRv6 and whatnot, but we'll only cover SRMPLS today. And our goal is to optimize the stamp processing for scale. So just a background, STAMP is a simple two-way active measurement protocol. It's an IPUDP probe packet with sequence number and timestamps. So the first measurement mode, one-way measurement mode in SR, where there is a sender, there's a reflector, packet goes from sender to reflector. We can measure one-way delay T2 minus T1 on the stateful reflector. So if you're using SR MPLS path, then in SR policy, SR MPLS policy in this case, we have a stamp session for each label stack of the SR policy. If it's a flex algo, then obviously you have flex algo label for the reflector. In case of measuring latency or loss for L3 service, now we have L3 VPN label. It's the same header that's used by the data packets. In this case, the IP header contains the addresses in the L2 VPN table. And same idea for L2 VPN label that's advertised by the reflector. So basically, idea is to use the same header that's used by the data packets. Two-way measurement mode. In this case, we get the reply back from the reflector to the sender, and now we have a one-way delay as well as round-trip delay. So there is some work done with the return path TLV, so you can use the TLV to come back on an SR path. The third mode is the loopback measurement mode. Loopback is basically a boomerang packet. We're trying to avoid the point and inject operation on the reflector to get the higher scale. The downside is that we only measure the loopback delay, T4 minus T1. So loopback basically, for SR MPLS path, you have full SR MPLS path to go forward and come back, or there's SR MPLS path to go to the reflector and then come back on the IP path with the destination as the sender. Similarly, for L3 service, you go on the service in the forward direction and then come back IP, or you have SR MPLS path in both directions. In case of L2 is the same idea. Only one trick I should mention for L2 VPN is that we use the trick of TTL is equal to 1 to punt the packet. So with loopback measurement mode, we take advantage now with the network programming, because if you remember, there is timestamp T1 and T4 only. So we can only measure round trip. But with network programming, we are able to collect the timestamp T2 on the reflector. So this way we have a one-way delay T2 minus T1, as well as loopback delay T4 minus T1. So this is made possible by the network programming. So for SR MPLS, how do we do it? We use MNA. There is a network action that's locally defined using, say, private opcodes. This is an informational draft, so there is no standard INI allocation requested. So in this case, it's locally defined network node behavior. It will just add timestamp in the packet on the reflector and forward the packet, just like a loopback mode. And depending on if it's SR MPLS or IP, your scope can be select or I2E. So we welcome your comments and suggestions. We are requesting a working group last call in spring, and we wanted to get your review comments from this working group. Thanks.
Yes. Hi, Greg Mirsky, Ericsson. Actually, I think that you might mention that this loopback mechanism is useful when there is not good quality of clock synchronization between nodes. Because this way, you can measure the round-trip delay and then deduce the one-way by dividing in half. So that gives you maybe better measurement rather than using unsynchronized clocks on your nodes.
That is true, yes.
Thank you.
There is an advantage, and I should have mentioned, is that you don't need the clock synchronization for this. Yeah, thanks, Greg.
So you mentioned you were going informational, but I think you're using ISD, and I think we've agreed that ISD is going experimental.
So this is it's a working group document and an informational document. I don't know the implication of a normative RFC that's experimental on the informational draft.
I think you have to also be experimental.
Yeah, it's something we need to discuss.
Any other comments or questions? Going once? Going twice? Thank you.
Thank you.
Next up is Yao Min.
Hello, everyone. It's Xiaomin speaking. This presentation is on the short update of the working group draft SPP for path segment. This is the definition for path segment. As MPLS path segment is defined in, I would say, 9545. So it's to uniquely identify an SR path on the egress node of the path. It's a single label that's assigned from SRLB of the egress node of an SR path. It's learned by owning the egress node and the ingress node of the associated path. The intermediate nodes of this path will not learn it. This is a recap of this draft. This draft defines 3 SPP target fact stack sub TOVs for path segment. And any of the 3 sub TOVs or 2 sub TOVs cannot be used in one SPP message because the 3 sub TOVs are used for different application scenarios. This draft had a working group last call between last IETF and this IETF. And this slide want to give an update on what's addressed during and after working group last call of this draft. To this MPLS draft, we have some small changes during the working group last call. Thank you, Greg, for your review and the comments. And to the PCESR path segment draft, there are some clarifications on whether and how the state of the path segment is populated at the egress node by the PSAP protocol. And to the IDR-SR policy path segment draft, Ketin has provided some clarifications on the mailing list. So thank you, Ketin, for your help. So what's still not addressed? It seems to the authors that all the requested clarifications on PSAP and the BGP have been provided. It's not preferred by the authors to escalate the references to PSAP and BGP drafts from informational references to normative references. And the authors would like to make all changes, if any, proposed and agreed by the working group. Okay, so can we send this draft to ISG? Thank you.
Greg Mirsky Erickson, thank you for the update and the summary of the discussions. So, couple points. Their applicability of proposed mechanism depends on the tail end of their SR policy being informed of their assigned SIDs. So my understanding that PCE document does ensure that there is this communication that through the PSAP, that both the head end and end tail will be informed, regardless of who allocates it. But that's not the case. Okay, so in my understanding, there are still some cases in if the policy is propagated, advertised through the BGP, then there are some still cases when their endpoint would not be informed of the allocated values. So only the head end.
Yes,
as
but
it
this
advertised.
chapter is only about path segment. If path segment is not used in your network, you don't need to have that signaling, right?
No, well, again, we can continue discussion on the mailing list, but as I understand that despite being used or not, if there is allocation so that only the head end will have this information, and there is a scenario when the endpoint will not have this information. So I wonder what will happen in this case, because then definitely since this fact is not known to the endpoint, the LSP ping will fail. So how that will be treated. So either we need to work with the IDR to enhance their document so that all scenarios, the BGP will inform the endpoint, or explain it. So in any case, I think that both specifications, PCE and IDR, are normative because they are required to be functioning in order for this tool to be useful.
I have explained on the mailing list why that's not needed. That's not necessary for the normative references.
Okay, then
Yeah,
then I guess we disagree.
we have to agree to disagree.
Yeah, we agree to disagree.
Ketan Talaulikar, Cisco, I just want to respond on that. So let's forget about the protocols, PSAP or IDR. This is a path segment, is a label that belongs to the tail end or egress. So that is the router. The egress is allocating a label from its own label space, and somebody has to tell it, maybe it's just via configuration, that this label is for certain SR policy. So this is a different from the normal SR policy because a state is being explicitly created on the endpoint and a context is necessary there. Either it is provisioned or via a protocol, but if we leave the protocol, it's still there on the segment. So I think it's not necessarily the context. I think that's what we want to match the FEC, right? So the context has to be there on the tail end. Now, coming to the protocols, PSAP has this request response and this elaborate mechanism that it can make this orchestration happen on both head end and the tail end. BGP is not that kind of a protocol. I won't go into whether it is even appropriate to do this in BGP. Let's leave that on the side. But I think let's progress this work with what we have. That's my view. Thank you.
Yes, so maybe I misunderstand something, but we are talking about not single fact here, but three facts. So it's not the SR policy identifier, it's a candidate paths identifiers for each multiplicity of candidate paths. And these candidate paths are not selected by the egress, they are selected by ingress. So that's what is being discussed and in question. Okay.
So this is the path segment RFC, which is in Spring. It allows for the path segment to be one for the entire SR policy. You could have it one per each candidate path. You could have it one for each segment list of a candidate path. That's the options that the path segment RFC.
Yes, that RFC has already defined all the three scenarios.
Right, but there again, since basically there are two possible sources of this information, that being PCE and IDR and BGP, and they are constituted different facts. Okay, so if IDR does not support synchronizing in state between ingress and egress of SR policy, then this is not useful because we cannot verify FAC, because the purpose of LSV ping is to verify consistency between the control plane and data plane status. So if the control plane between ingress and egress is out of sync, so what we can verify then?
Okay, so first, the solution does not at all require a control plane whatsoever. Yeah. It can be just done by static provisioning. And there, depending on, let's say the operator wants the path segment on one of these three schemes that we discussed, they would actually need to go on the egress and say, ask the egress to allocate a label for this context. And then they need to, whatever label is there, they need to go and provision it on the ingress. And of course, LSP ping can then verify that it is okay or not. So that's the management plane option. We do have one PSEP control plane option, which is defined, which will do that. Now, I agree with you that IDR doesn't do the signaling, the BGP doesn't do the signaling, but I'm just, as I said, maybe I'm repeating myself. I'm questioning whether BGP is probably the right or the best way to do this. But I hope the other two at least make a case for this to progress forward.
Okay, so again, this document defines multiplicity of facts, and the differentiation of these facts is not only on the character, whether it's a SR policy candidate path or else, but on the source. So if we believe that IDR is not capable of synchronizing the state between ingress and egress, that has to be excluded from the facts. So basically, if it's unreliable, then there is no way of reliably verifying the consistency between the control plane and data plane if the source of this FAQ is IDR. If we introduce another type of configuration in addition to PSAP, to PCE, and saying it's a management plane, that is a new distinct type of FAQ. Okay, so in any way, in my opinion, this document needs some rework.
Just the last thing. For me, FAQ is a context, and it's independent of the signaling protocol, but that's fine. I mean, if we want, we can add something more to the context, but I think I'll leave it to the authors and others in the working group.
Gentlemen, can we move on, please?
Yeah, but I believe that if we look back in the history of FAQs, we have LDP FAQ, RSVP FAQ, and so and so and so. So historically, it's been a part. If we decide not to, okay, let's discuss it and make it regardless of the source.
All right. Our next presentation is deterministic network-specific M&A. Craig Mirsky.
It works.
I think so.
Let's try. Okay, hello. Greg Mirsky, Ericsson. I present this new proposal for M&A. And so on deterministic networking, what is deterministic networking? The intention of deterministic networking to use existing techniques, providing low packet loss rate and bounded latency in a limited domain. So for that, we identify two sublayers in the DetNet, and you can look at the DetNet architecture. There's a forwarding sublayer and DetNet service sublayer. Their data planes on the forwarding layer of the DetNet is IP or MPLS, and the service sublayer is to use techniques as a packet replication, duplicate elimination, and ordering functions to improve on-time delivery and low packet loss. So for the MPLS data plane, currently it uses the pseudowire solution. but we can think of on the DetNet service sublayer as more of the multi-segment pseudowire. And one important thing that before we start looking at how DetNet operates, so to be predictable, it doesn't use, prohibits use of load balancing in equal cost multipath. So basically it has to be explicit routing. For the DetNet with the MPLS data plane, you can see here what the stack will look like for data packet. So we have forwarding labels, and we have bottom of the stack label, which identifies the DetNet flow, and then we have DetNet control word. DetNet control word, again, it's a variation of common control word for the pseudo wires. And we define the DetNet control word and DetNet associated channel header, because for the DetNet service sublayer, we need to have a sequence numbers so that packets replicated and eliminated based on the sequence number information. In a way, how this is used in the DetNet, it's well, probably closest analogy will be 1+1 protection. So there a replication function, as it comes from the name, sends a copy of the packet with the same sequence number on alternative path. So somewhere downstream, there is a place of duplicate elimination function that basically lets the first packet with a given sequence number through, and if it sees later a packet with their same number, so that packet is eliminated, it's dropped. So in a way, it's active protection, but on a packet by packet based. So the first, whatever comes in, got through. So which is different from 1+1 protection, where we choose the working path and then we have a backup path. If we detect the failure on the working, we switch over and we'll take a sync input from difference. So now we will look at the problem with their OAM, with active OAM. So because we need to use ACH, so with the first nibble is different, and it includes version. So the sequence number space is smaller. So thus, basically, their data packets and active OAM packets that belong to the same flow, or actually we use OAM to monitor that given flow, DetNet flow, they will have a different separate sequence spaces, which is sort of inconvenience. So now we look at M&A, and M&A gives us an opportunity to use a single sequence number space, both for data packets and active OAM packets that belong to the same DetNet flow. So here's an example of how that all the options, all the information that useful for DetNet can be combined and expressed using M&A. So we believe that ISD M&A is quite suitable because this is a very limited footprint that we need to. And actually, you will notice, because as I mentioned in the opening, so that in the DetNet, the use of load balancing is prohibited. So because of that, the issue of mutability of the label stack doesn't exist. It's non-issue for DetNet application. So because of that, it would be acceptable to do the variation between of the fields information that is included in M&A, DetNet M&A, from packet to packet. also even within the packet, because, for example, one of the application is proposed here to have expressed latency budget for the packet to be propagated. Because in some .NET applications, for example, as for industrial automation, packet needs to be delivered within bound. So if this bound is expired, the packet is good as being dropped somewhere before it even delivered to the destination. So that can be achieved using this. So that is our proposal. We welcome your comments, and we'll be happy to work with your comments and collaborate. And then when we converge and advance, then we'll be asking for working group adoption.
So Lou Berger points out on the chat that .NET MPLS says ECMP is not recommended, not prohibited.
Okay. Actually, I think that, okay, I think that I can see somewhere, I think somewhere in the, not, okay. 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 Yes.
Xie from ZT. Thank you, Greg, for your presentation. It's very happy to see you also have interest on this topic. As you know, we have a draft. It's also about M&A for .NET support. Actually, we have presented for several times. At last meeting, we presented both in both MPLS working group and .NET working group. From my perspective, what I can say that there's some overlap between these two drafts. So it may be a good choice for us to work together to address this question. And my another concern is about in your draft, you propose to use M&A to support the traditional .NET functionalities, to encapsulate flow ID and sequence number information. I'm not sure whether there's necessity to create a new method to support the traditional functionalities. Yeah, it's my concern.
Mm-hmm. Yes. So actually, if you look, so this is an example, and these three options, so M&A opcodes, they can be combined as needed for their different deployment. One of the advantages and one of the goals that we had is that to have single sequence number space that can be used by data packets and active OEM packets that monitor the same flow, because that would significantly simplify their use compared to their pseudo-wire-based .NET instantiation. So definitely we'll be going to .NET working group to discuss this. Either this approach is something that is relevant, but in regard to working together, yes. So let's have this discussion and see how we can collaborate.
Okay, thank you.
Okay, so I'm saving for almost 5 minutes.
All right, we have quite a bit of time left. I know I had to cut off some other conversations. Mic is now open. The mic is open, any topic. Well, okay, please stay out of US politics.
Okay, so then I would go back to the second presentation by Fabian. So, and again, I understand that probably too specific for P4 architecture, that the depth of the of the stack, LSC. Is it the same would be for the buffer, the fast forwarding buffer that will limit? Because one of the concerns that I have with the post-stack data approach in M&A, that by putting their actions, M&A actions, information, and ancillary data post-stack, makes it even more challenging for the fast processing, line rate processing. Because, for example, even in the case of, even if it's a pure PSD, so, okay, because if it's a combination of in-stack data and post-stack data, it can be terrible. But if we have a MPLS of reasonable detailed information, like strict routing on a number of nodes, so putting M&A in the post-stack data, so probably increases the chances that that will be out of this fast buffer. So thus the processing and this action on this M&A in the post-stack data will be even more challenging.
Yes, thanks for that comment, and it's actually correct. Because for our post-stack implementation, we've seen that like we have an RLD of 51 LSEs, and with the post-stack, that also means that we need 51 LSEs, including the post-stack. So we have two versions right now, a hybrid version that has maximum sized NAS, I think. It's a long time ago that I did this. And that in between stack is basically shrinking to 0. And then we have like 16 LSEs for post stack, but that's not really feasible as we have nothing in between there. And we also have a pure post stack implementation, but pure in case of we still have in stack network actions that indicate the presence of post stack, like using the YAX draft with the p-bit. And there we defined the constraint. Either we have only one NAS at the very bottom of stack that indicates post-stack data, or we restrict the size of a NAS to 2 LSEs only because that's the minimum we require to indicate the p-bit. And even then, that's a lot of overhead for just indicating post-stack data.
Thank you. Actually, some questions come too late. Maybe this is not too late. So one of the maybe interesting scenarios to consider is that in some services, they already will have post-stack header like pseudowire or beer. So that's the PSD will have to go lower than post-stack header prior than a payload. So that might be another like monkey wrench to throw, so which make it even more challenging. But it will be interesting because then beer probably will be the most severe case because they have a, as it comes from the name, it's a bit indexed, and they have probably some of them like quite long bitmap for their nodes to make it scalable. I don't know, probably their default to 56 or 512 bits. So their header will be quite sizable. Then the space left for PSD will be very limited. Thank you.
So one comment, and maybe it's a request. So in the post-stack solution draft, in the in-stack, it says that there's a post-stack data and there is an offset. It says that it's located maybe say 54 bytes down. Using that, will it help with the RLD problem? So if it says this is outside my RLD, I can just skip it and things like that. So when you are evaluating or experimenting with post-stack, see if that that kind of offset is helping or making it worse. So that kind of feedback would be useful.
Well, I can only speak for the P4 side, like the P4 implementation, and working with offsets is really painful there. So I think it might make the implementation even worse. I haven't implemented it yet, but it's not that easy to do, honestly.
Any other comments, questions, discussion on anything at all? All right. Thank you very much. See you in Bangkok.
Jim wants to talk.
So I don't even know if we need to have a conversation. I was just wanted to make sure that we're good. So, like initially, I wanted the conversation to the M&A header document. It seems like you've got that under control.
So we're doing PSD.
Yeah.
M&A header document. Noise about doing experimental is overwhelming. We clearly need to go that direction.
Yeah, I was wondering on the header document